Okay, one more projectile example here. We're going to deal with the situation where the object is going to land higher than it started in the first place. Soccer ball is kicked off the ground and lands on a hill that is 1.8 meters above the original ground level. The ball's initial velocity of 8.0 meters per second, 65 degrees above the horizontal. Determine the horizontal range and the impact velocity. Here I'm going to show you a little trick that will let you avoid the quadratic equation if you haven't figured out how to use your calculator to avoid it. So here's the situation. Here's your soccer ball. Here's the ground. You're going to kick it up at 8.0 meters per second, 65 degrees, and it's going to land on a hill or something, and that hill is 1.8 meters tall. So again, this is a pattern here with these ones where we have an initial velocity that is on an angle. Our first step before we can even get started is to divide that into components so we can deal with our horizontal direction and our vertical direction separately. So this is our opposite side, which means it's going to be 8 sine 65, which is 7.25 meters per second. In this, our adjacent side is going to be 8 cos 65, which works out to 3.38. So there we go, that's the initial velocity in the vertical and horizontal direction totally separately. And with those in hand, we can start dividing up our information separately. In the vertical direction, I have an acceleration of negative 9.8 meters per second squared. In my horizontal direction, I have an acceleration of 0. I have an initial velocity of 7.25 meters per second. I have an initial velocity of 3.38 meters per second. And here I have a displacement. The ball's going to land a distance 1.8 meters higher than where it started, so of 1.8 meters. Now the trick to avoid using that quadratic that we dealt with in a previous example is to find the final velocity here first. So I'm going to deal with that one first. That means I'm going to use the equation 2AD equals V2 squared minus V1 squared. So 2 times 9.8 times 1.8 is going to give me 35.28 meters squared per second squared, and that's a negative. .25 squared is 52.56 meters squared per second squared. I'm going to bring that minus 52 over to the other side. It becomes a plus, so I'm going to say V2 squared is equal to 17.28 meters squared per second squared, and then I square root here. And remember, this is again one of those situations where I have to introduce the negative and positive. I got to be careful about that. So I'm going to get 4.16 meters per second when I square root, plus or minus. But imagine this ball coming up and coming back down. When it's coming back down, its vertical velocity is negative, representing the negative direction, or in all of these projectile problems, I'm using down as negative. Okay, so I might as well finish off with impact velocity. I had a horizontal impact or horizontal initial velocity of 3.38 meters per second and an acceleration of 0. What that means is this is also v2. Acceleration is your change in velocity. You're saying 0, so you're saying your velocity isn't changing. v1 is v2 is 3.38. My new vertical velocity is coming down at negative 4.16 meters per second. So I can use my Pythagorean resultant. And I can put the negative on this. I wouldn't mind if you didn't put the negative on this because you recognize it's just going to get squared away. But, you know, just being really thorough, you can put it on there. .36 is your sum here. And looking for theta, I can recognize that this is my opposite and this is my adjacent. Remember, it points to opposite. So tan theta is equal to your opposite over your adjacent, which is 4.16 meters per second and 3.38. And again, because I'm going to use a heading or something else to interpret the direction of this thing, I'm going to just use absolute values in this and get that angle, and then I'll sort out what that angle means. If you're finding your calculator is giving you funny results for these inverse tan functions, it's worth making sure that your calculator is set to degrees. I'm using degrees for all these questions. You can use radians, of course, if you want, but the common thing to do is to use degrees, and so we need to make sure we're all on the same setting. So I get an angle of 50.9 degrees. Again, I can interpret that as 50.9 degrees below the horizontal, or if I want, I can say x negative 50.9 degrees y. So as I said, I started in the x direction, I went towards the negative y direction. That sort of takes into account that negative, but it interprets it in a heading way that's just a little bit clearer, I hope. Okay, so that's the impact velocity. That's that. And we haven't done the horizontal range yet. Let's go back to here. This is when we had all given information about the question. Remember the acceleration negative 9.80. We've got initial velocity. We've got two things in the horizontal direction. This time in the vertical direction, what we want is time. And the reason is we can apply that time in the horizontal direction and solve our problem. But now we know what V2 is. V2 worked out to be negative 4.16. What that means is I have more given information to work with. I always have to be careful using given information I came up with myself, but to avoid a quadratic, it might be worth it. Here, if I use A, V1, and V2, I can come up with an equation for t that's easier to solve than that quadratic, and I can do the problem a little bit more simply. Acceleration equals V2 minus V1 over t. Oh, my last problem's encroaching on us here, so let me get rid of some of this stuff. And that's all divided by t. So 4.16, I'm down, and I'm down even worse, 7.25. So I'm down negative 11.41 meters per second here over t, negative 9.8 meters per second squared. And never forget, when you have a variable on the bottom, Assuming you can trust that variable not to be 0, you can multiply both sides by the variable, and that allows it to cancel out, and it gets it to the top where you can solve for it. From a math perspective, if that variable can be 0, then we could have just created some problems, but assuming here we're not interested in a solution where t could be 0, we can sort of ignore that. So what we got here is that for the velocity to change from 7.23 to 4.16 under an acceleration of 9.8, that would take a time of 1.16 seconds. But possibly most importantly, what we did is we used the impact velocity information that we gathered in this problem to solve for the time, and we didn't have to do a quadratic. And since we didn't want to do a quadratic, that's great. So now we got a time, we got an initial velocity, we got an acceleration, and we're still working towards our horizontal range. So it's our displacement in the horizontal direction that we're solving for. What I'm going to do right now is I'm just going to sort of go to fresh space where I can write, but I will bring down all this information when I have it. So the equation, I have my displacement, I have my initial velocity, I have my time, and I have my acceleration. My acceleration is 0, so I can sort of ignore that term. Actually, I'll just write this out properly. My V1, let's go all the way back up here and look at it, make sure we get it right. 3.38 meters per second. My time, 1.16 seconds. Plus 1/2, my acceleration is 0, t squared. So this whole term, if there's a 0 in it, goes to 0. So I just have to multiply those two things. I got 3.94 meters per second. Not meters per second, because I have a meters and a meters per second, just meters. So there you go, there's my horizontal range. And there is an example of how, if you have to calculate the impact velocity anyway, you can use your calculation for the impact velocity to avoid the quadratic that results from when you have a projectile that has a change in height as well as an initial velocity. A quick note here, I nearly forgot to say this for the other video as well. Your impact velocity here was 5.36 meters per second. Your initial velocity was 8.0 meters per second. So in previous questions, I feel like we said that the impact velocity and the initial velocity for projectiles is the same. And it doesn't work out to be that way in this case. If you recall the last video, it didn't work out that way either. The trick to that is that the impact velocity is only the same as the initial velocity when the projectile returns to the same height that it took off from. Imagine this object flying through the air and landing up here. I think you can see, just looking at this quadratic, that it's going to come in slower than it took off. It's only when it returns to the same height that it took off from that the symmetry tells you that the initial velocity and final velocity should be the same. So the magnitude of the V1 is only equal to the magnitude of the final, or the initial or the final, if the projectile returns to the same height. Or if you prefer to think about it this way, if delta D vertical is equal to 0. So that explains why the last two final velocities have looked the way they have. That's all for projectiles. So that's the end of the video.